Now that we've taken a look at how a system of differential equations can be set up as a matrix, we're ready to answer the question, how do we solve systems with matrices? And to kind of look at how we solve them, we're going to look at a very slow example so we can see the details of what's going on as we study the process that's going to be used to solve a system of equations. Now, we need an example to work through with this. So let's just use x prime is equal to 4x plus 2y, and y prime equals 3x minus y. All right. We already know how to take that and make it into matrix form. We would say capital X prime is equal to the coefficient matrix of 4, 2, 3, negative 1 times our solutions matrix X. Well, in order to solve this system of equations, what we're going to first do is find what's called the eigenvalues. For those of you that haven't taken linear algebra, eigenvalues are a special value related to a square matrix. And we're going to find those eigenvalues by placing a minus lambda on first diagonal and find when the determinant is equal to 0. What do I mean by that? Well, what that means is we're going to take this matrix that we found, the 4, 2, 3, negative 1, and we're going to subtract the lambda from this first diagonal, the 4 and the negative 1. So we're finding the determinant of a 4 minus lambda, 2, 3, and negative 1 minus lambda. And we want to know when that determinant is equal to 0. So first, to find the determinant, we can take 4 minus lambda times negative 1 minus lambda. And I subtract the other diagonal, which is 3 times 2 equals 6. And we want to know when that determinant is equal to 0. Well, we can multiply this out. 4 times negative 1 is negative 4. And then we've got a negative 4 lambda. Then we've got a positive lambda and a positive lambda squared minus 6 equals 0. And if I combine like terms, that's lambda squared minus 3 lambda minus 10 equals 0. We can solve for lambda by factoring. And we've got lambda minus 5, lambda plus 2. So I can see that lambda equals 5 and negative 2. These are the eigenvalues. Now, if you want to really look at eigenvalues, you can take a full linear algebra course and work with eigenvalues. This is as deep as we're going to go with it on this course. But each of these eigenvalues has a special vector with it called the eigenvector. Let's take a look at how we can find the eigenvectors. So the second step we're going to do when we're solving is we're going to find the eigenvectors. And to find the eigenvectors, we replace our lambdas with what we found them to be equal to, 5 and negative 2, and multiply the matrix by a matrix AB and set equal to 0. So here's what I mean by that. So if lambda equals 5, I've got this matrix up above, 4 minus lambda, 2, 3, negative 1 minus lambda. And that's going to become, if lambda equals 5, 4 minus 5 is negative 1, 2, 3, and negative 1 minus 5 is negative 6. And we're going to take that matrix and multiply it by our AB. Using matrix multiplication, multiplying the first row by the first column, that's going to give me negative A plus 2B. We said we wanted to set it equal to 0. In the second row, we've got 3 negative 6 times the AB. So that's 3A minus 6B equals 0. Now, this system of equations always has infinite solutions. Usually one equation is a multiple of the other equation. So what I'm going to do is I'm going to choose one and solve for either A or B. Now, I always choose the one that looks the simplest. So for me, in this case, I think this first one looks simpler. And if I add A to both sides, I get 2B is equal to A. And that will give me the relationship between A and B. Then on the more complex side, I'm going to pick a value that's really convenient for B. I can pick any value I want. We want to pick a non-trivial value, so we don't usually pick 0. But what I usually do is pick 1. If I let B equal 1, then my matrix AB, A is equal to 2B, which is 2, and B, we said, was 1. This 2, 1, then, is the eigenvector for the eigenvalue of 5. Now, it could look different depending on who did this, because if you had picked the number 7 for B, A would have been 14, and you would have a different looking vector. But each eigenvector is a constant multiplier or a scalar multiple of each other. So you can pick whatever you want for B, and it'll still give you a valid eigenvector. I always just pick an easy, convenient value. Now there's a second eigenvalue that we need to work with, so let's find the second eigenvector. The second eigenvalue was lambda is equal to negative 2. And if I remember, you have this up above on your notes. It's off my screen, so I'm just going to write it here. We had 4 minus lambda, 2, 3, and negative 1 minus lambda. So when I plug in negative 2 into that, I'm going to get the vector 4 minus a negative 2, which is 6, 2, 3, negative 1 minus a negative 2, which is 1. And then we multiply it by the eigenvector of AB. What's that equal to? Well, we get 6A plus 2B equals 0. And 3A plus B equals 0. I can pick either of these equations because one should be a multiple of the other. I think the second one looks simpler. And if I subtract 3A from both sides, I get B is equal to negative 3A. So now on the complex side, I'm going to pick a value for that side. Let's let A equal 1. That's just a convenient number. If A is equal to 1, we end up with A is 1 and B is negative 3 times 1, which is negative 3. And we've got our eigenvector of 1, negative 3. Once we have our eigenvalues and our eigenvectors, we actually are ready to solve the system. As we found out last time, we can make a general solution once we have two linearly independent solutions to the system, because we have two derivatives. So it's going to be x is equal to our first constant times the first eigenvector, e to the eigenvalue times t, plus the second constant times the second eigenvector, e to the second eigenvalue times t. And you'll notice this is very similar in form to what we found with linear differential equations. in one variable. We would have c1 e to the derivative, the solved derivative times t, plus c2 e to some power times t. It's the same exact idea, we're just working it for the system of equations. So from above, just because it's off my screen, we found out that when lambda equals 5, the eigenvector was 2, 1. And we found out when lambda equals -2, the eigenvector was 1, -3. And so we put that together to get our solution, that x is equal to c1 times the first vector, e to the first eigenvalue times t. So c1 times 2, 1, e to the 5t, plus c2, vector 1, -3, e to the -2t. And this then is the solution to our system of differential equations. What you find is that using the eigenvalue method, it's much easier to identify the solution than it was using the elimination method, because we had to find this relationship between all the constants, and that got kind of ugly. So that's kind of nice about the matrix method, is it is a lot more of a direct way to get to a solution. So let's try an example. And we're going to even solve for the constants in this example, just so that we can see how a full solution can work out. Let's say x prime equals 4x minus 3y, and y prime equals 4x minus 4y. And we have some initial conditions that x of 0 equals -1, and y of 0 equals 2. We're going to come back to those initial conditions at the end to find what the constants are. But we can change this into matrix form as x prime is equal to 4, -3, 4, -4 times our x. All right. First, we're going to find the eigenvalues. So we need to know when 4 minus lambda, -3, 4, and -4 minus lambda is equal to 0, the determinant. So that gives us 4 minus lambda times -4 minus lambda minus -3 times 4 is -12. So we now have a positive 12 equals 0. Multiplying this out, we get -16 minus 4 lambda plus 4 lambda plus lambda squared plus 12 equals 0. Combine like terms, lambda squared, 4 minus 4 is 0, that's nice. -16 plus 12 is -4 equals 0. And so it factors to lambda minus 2, lambda plus 2 equals 0. So we now know our eigenvalues are 2 and -2. Now we can go after our eigenvectors. For lambda equals 2, we're going to plug 2 in for the lambdas. And so we get 4 minus 2 is 2, -3, 4, and -4 minus 2 is -6, times our eigenvector of AB. That's what we're looking for. So we get 2a minus 3b equals 0. 4a minus 6b equals 0. I'm going to go with the first equation, looks simpler to me. Add 3b, 2a equals 3b. And then let's divide by 2, so we can say a is equal to 3b divided by 2. I can pick any value I want for b. Let's pick something convenient. If I have to divide by 2, let's make b equal to 2. So if I make b equal to 2, a is going to be 3 times 2 is 6, divided by 2 is 3, and we said b was 2. So our first eigenvector is 3, 2. Let's then figure out what happens when lambda is equal to -2. Well, 4 minus -2, again, I'm plugging the -2 into the lambdas, gives us 6. -3. 4. -4 minus -2 is going to be -2 times our AB. I'm running out of space, so let's just go below, I guess. So we've got 6a minus 3b equals 0, and 4a minus 2b equals 0. I'm going to say the bottom one looks a little simpler. So 4a equals 2b, and I can divide both sides by 2 to avoid fractions. So b is equal to 2a. I can pick any value for either of the letters. So I'll pick the more complicated looking side. We'll let a equal 1, which is going to give me 1 for a. 2 times a is b, which gives me 2 for b. And my eigenvector is 1, 2. Put that all together to get our solution for x. X is c1 times the vector 3, 2 times e to the 2t plus c2 times the vector 1, 2 e to the -2t. But we're given these initial conditions. We were told that x of 0 equals -1 and y of 0 equals 2. So let's look at how we can use that to find out what our constants c1 and c2 are. Well, remember, x is really a matrix representing x of t and y of t. So just going across the top, the x of t is equal to 3c1 e to the 2t plus 1 c2 e to the -2t. And going across the bottom, the y of t is equal to 2c1 e to the 2t plus 2c2 e to the -2t. Plug those values in that we were given. X of 0 is -1 equals 3c1 e to the 0 is 1 plus c2. For the y of t, it equals 2 when the t is 0. Plugging in 0, we get 2c1 plus 2c2. And then all we have to do is go back and solve for c1 and c2. I'm going to do that by multiplying the first equation by -2 on both sides. That's going to give me 2 equals -6c1 minus 2c2. Adding the equations together, we get 4 equals -4c1, which means if I divide both sides by -4, c1 equals -1. Figuring out c2, I'm going to plug it back into the original equation. So I have -1 equals 3 times c1 plus c2. -1 equals -3 plus c2, so c2 is equal to 2. So now my solution is x equals c1, which is -1, times 3, 2, e to the 2t, plus c2, which is 2, times 1, 2, e to the -2t. I could probably stop there, but let's clean it up. Let's multiply that scalar into the matrix, which is going to give us -3, -2, e to the 2t, plus 2, 4, e to the -2t. And that becomes our final solution to the system of equations. Eigenvectors and eigenvalues might be a little new if you haven't taken linear algebra, but once you kind of get used to the process of putting in that lambda, solving for it, picking some value for A or B, and then figuring out the relationship to the other one. Solving these using eigenvectors and eigenvalues is much easier than the elimination methods. We want to get really good at this, and we're going to complicate things a little bit in our future videos. But right now I want you to get really good at this process. So take a look at practicing. Let me know if you have any questions, and we will see you in the next video.